Okay, let's talk about some recurrence relations. So in class, I might have talked already about this particular recurrence relation. If we take, so let's say Rn is equal to the number of regions in the plane formed by n non-parallel lines. So in particular, R0 is 1 because if I just take no lines, then the plane is one region. If I take R1, so if I take one infinite line in the plane, so this is these lines go off to infinity in both directions. So they're not line segments, but they're full lines. So R1 is going to be 2 because when I draw one straight line, it breaks the plane into two regions. Now think about what happens if I have n lines and I add another line. Okay, so since these lines are not parallel, for example, when I have one line and I add another one, it's going to cross that line, the original line, exactly once. Okay, and when it crosses that line, it creates a new region, right? So basically, in other words, before I add that line, I had, this down here was a solid kind of region. We broke it in half when we created the line, and then we broke the other region in half as well. So okay, I mean, if we just, kind of clearly, R2 is going to be 4. Now let's think about when we add another line. So, so I should say these are non-parallel lines, no three lines meet in a single point. So when I add the third line, I'm not allowed to run it through that middle point here. So it must, again, it must cross this line somewhere, and it must cross the other line in some unique point. And if you think about it, when it crosses the first line, that creates a new region. When it crosses the second line, that creates a new region. And then when it goes off to infinity, that creates a third region. If you think about it in general, we're going to have this recurrence that Rn plus 1, when I add the n plus 1th line, I have all the regions, so I've as many regions as I had before, plus the number of new regions, which is going to be n plus 1. Because if you think about it, I start my line off at infinity. When it reaches the first previous line, I create a region. When it reaches the second one, I make a region, so on and so forth until it reaches the nth. And then when it goes off to infinity again on the other side, it makes another region. So in general, you have Rn plus 1 is Rn plus n plus 1. So you might be wondering, what is the closed form expression for Rn? Okay, in this case, it's not actually that hard to do. But what I want to show you is a really nice trick for working out in this case. And then we're going to look at other recurrence relations, which can also be solved with this trick. So the trick for doing this is going to be to set up a telescoping sum. Okay, so if you aren't familiar with a telescope, it's one of these things, right? One of these things where you can look at and stretch it out and see for a long distance. So here's a kind of picture of what a telescope is. So let's, how do I make a sum that looks like a telescope? Basically the idea is you have a long sum of numbers which are written where each number is written as the difference, so a subtraction of two numbers. And the telescoping is that there's going to be some sort of cancellation that happens, which allows you to shrink that long sum into a small sum. Okay, let's see how that works. So we've got this region thing. So let's actually write it in terms of, so let's write Rn in terms of Rn minus 1. Okay, so this is equivalent to the recurrence relation we wrote before, right? So our recurrence was generally that R0 is 1, and let's say Rn plus 1 is Rn plus n plus 1 for n at least 0. But you could also write it like this. So you can also say Rn is equal to Rn minus 1 plus n for n at least 1. Of course, these two ways of writing it are exactly the same. Okay, so take Rn, and so we can actually write this in a slightly better way. So let's put the Rn and the Rn minus 1 on the same side of the equality. So in other words, if I pull over the Rn minus 1 to the other side, I get that the difference Rn minus 1 is n. Okay. So imagine n is some large number. So if n is large enough, I can do this again. So I can write Rn minus 1 minus Rn minus 2. Right? And the way that the recurrence works is that this should be equal to n minus 1. Right? And then Rn minus 2 minus Rn minus 3 will be equal to n minus 2. Okay. And we can keep going, right? So generally, we can, if we go to any kind of k, rk minus 1, we can write as k. Now that's going to work all the way down to R1 minus R0 equals 1. Okay. And obviously we can't keep going because, there's no such thing as R minus 1. So we have to stop here. Here's the trick. Let's sum up both sides of this equation. So if I sum the left side, well, first of all, if I sum the right side, that's going to be, so if I sum up the right side, it's kind of simple. It's just the sum of k equals 1 up to n of k. The cool thing is what happens when you sum the left side. You get a bunch of cancellation, basically. Right? You see, here I've got an Rn minus 1 being subtracted, and on the next line I have an Rn minus 1 being added. So these are going to cancel when I add them up. But then similarly, you've got some more cancellation. So Rn minus 2 is going to cancel with this Rn minus 2. And the Rn minus 3 here is going to cancel with an Rn minus 3 on the next line, which I haven't written. But, this goes all the way down to, so on the second to last line, we'll have R2 minus R1, and the R1s here cancel, right? So the only thing that actually remains after you add this all up is the minus R0 at the end and the plus Rn at the beginning. So this is something which is known as a telescoping sum. It's a sum of the form, Rn minus Rn minus 1 plus Rn minus 1 minus Rn minus 2, minus Rn minus 3, and so on. And you can kind of think of you have this long sum, which is, think of that as like a long telescope. And if you think about it, you can kind of push it together, like kind of click it all together by canceling out the intermediate stuff. So that cancels, and that kind of clicks together the telescope, and you're only left with Rn minus R0. So Rn minus R0 is equal to this, which we know what this is, right? If you sum from 1 up to n, we proved this back when we did combinatorial arguments. So this is n times n plus 1 over 2. So we get that Rn is equal to, so what we had from the previous slide was Rn minus R0 equals n times n plus 1 over 2. R0 is just 1, so we can just solve for this. So therefore, Rn is n times n plus 1 over 2 plus R0, which is n times n plus 1 over 2 plus 1 for all n at least 0. Okay, so this the telescoping trick that I've done here is really useful for order 1, so first order. It's really useful for first order recurrence relations. It's not going to be very useful for second order recurrence relations, but that's okay. We'll find other methods to solve those. Okay, let's look at a slightly more involved example, or just a slightly different flavor. So let's say that A0 is equal to, I don't know, 7, let's say, and that AN is equal to, I don't know, 5 AN minus 1 plus, I don't know, what's your favorite number? 8, I don't know, for all n at least 1. Okay, so let's start by setting it up like before. So we're going to take our recurrence kind of equation here. And I'm going to put the AN and the AN minus 1 on the same side. Now we want to set up this telescoping thing. If we try to do that the same way as before, it's not quite going to work. So if we just write AN minus 1 minus 5 AN minus 2 equals 8. So this is correct. However, if I add everything up on the left side, it's not going to completely cancel, right? Because here I've got just an AN minus 1, and here I've got 5 AN minus 1. So in order to cancel, I actually kind of want to take the second equation and multiply it by 5. If I multiply it by 5, it's still a true equation, right? So 5 times this thing is equal to 5 times 8. And now you can see you're going to get the cancellation that you want between the first line and the second line. Now let's write down our next line, AN minus 2 minus 5 AN minus 3 is equal to 8. And again, we can see that this is not going to cancel because here when I multiply out the 5, I have a 25, like a 5 squared AN minus 2. And here I've got a measly little AN minus 2 with no coefficient. But we can solve that the same way, right? We just multiply this equation by 5 squared. And now it's going to cancel. And generally speaking, if I take, let's say, AK minus 5 AK minus 1, if you can kind of see the pattern that what I want to multiply this by is 5 to the n minus k. And that should equal 5 to the n minus k times 8. Dot, dot, dot. Let's look at, for example, a2 minus a1. So that'll be all multiplied, or sorry, by minus 5a1. That'll all be multiplied by 5 to the n minus 2. And then that's 5 to the n minus 2 times 8. The very last line is 5 to the n minus 1, a1 minus a0, and that's equal to 5 to the n minus 1 times 8. Okay, so if you think about it, when you sum this all up, this is going to cancel with this because I've got a 5 out in front. This whole thing is going to cancel with this because of the, it's going to be 5 squared, an minus 2 on the second line, and I've got a 5 squared here, and so on and so forth. So all of these kind of cross terms cancel out. So this will cancel out with this. And at the end of the day, all that's left over is so you have to remember this. I've got my 5 to the n minus 1 a0. I've got my an, and I've got to sum the right hand side as well. So let's do this over here. So an, you got to think about what's going on here, but it's going to be a minus 5 to the n minus 1 a0, I think. Yep. Equals 8 times the sum from k equals 0 to n minus 1 of 5 to the k. Now this is where we need to remember some of our stuff from generating functions. So remember that if I sum from, let's say, k equals 0 to infinity x to the k, that's supposed to be equal to 1 over 1 minus x. Now this here, of course, is not an infinite sum. It's a finite sum, but if you take the sum k equals 0 up to n minus 1 of x to the k, well, that should equal the entire geometric series minus x to the n over x to the n over 1 minus x. Right? And if I think about this thing and I plug in x equals 5, we should get that the right-hand side here is 8 times 1 over 1 minus 5 minus 5 to the n over 1 minus 5, which gives you 8 times 5 to the n minus 1 over 4. So that's just a bit of algebra. Okay, so now we have a formula for an, right? An is going to be equal to, well, a0 is 7. So if I move this over to the other side, I have 7 times 5 to the n minus 1 plus, so 8 over 4 is 2. So 2 times 5 to the n minus 1. Okay, and you can do some more algebra here if you really want to, by trying to combine the 5 to the n's or something like that, but you don't really have to if you don't want to. So this would be a totally acceptable final answer. Okay, so this is, yeah, like I said, this is just a very nice trick for solving first order recurrence relations. This gets it gets a little bit weird when you're dealing with negative numbers. So let's do one more example with negative numbers, and then that'll be the end of this video. Okay, so say that b0 is equal to, I don't know, 42, and that bn is, Well, let's do a more challenging example. So bn minus 1, or sorry, so 3 times bn minus 1 plus, or sorry, negative 3 bn minus 1 plus n. Okay, once again, just set up your good old recurrence formula here. So bn plus 3 bn minus 1 is equal to n. Okay, all I've done here is I've moved the negative 3 bn minus 1 to the other side. Write down the next case, bn minus 1 plus 3 bn minus 2 is n minus 1. However, this is not going to cancel, right? So we've got the same issue as before, but now you see that I don't want to multiply this by like a 3 because that's still not going to cancel. I need to multiply this by negative 3. So I multiply both sides of the equation by negative 3. And now you can see that when I add the first line to the second line, the bn minus 1 is going to cancel. And now let's do that again. So bn minus 2 plus 3 bn minus 3. And on the other side I have n minus 2. And here it's a good idea to multiply by negative 3 squared. So essentially the number that ends up here is just going to be whatever was here to the appropriate power. And so on down to negative 3 to the n minus 1 b1 plus 3b0 equals negative 3 to the n minus 1 times 1, I believe. Okay, sum both sides, and on the left side you get bn plus negative 3 to the n minus 1 times 3 times b0. Okay, I think that's correct. And on the right side, this is going to be the sum. K equals, let's say, 0 up to n minus 1 of negative 3 to the k times n minus k. Okay, so therefore, I now have a formula for bn. It's not great because I still have a sum, but if I can take bn here, I can subtract this to the other side, and I've got a formula. So let's try to simplify further after doing that. Okay, so I want to subtract it over to the other side. So my negative 3, my positive 3 here actually becomes a negative 3. And what I end up with is something like this. So maybe let me go back for a second and show you what the original equation was, and then we can maybe feel a bit more justified with this. So my original equation, I had bn plus this thing, negative 3 to the n minus 1 times 3 times b0. If I move that to the other side, I'm subtracting it to the other side, which is the same as basically putting a negative 3 instead of a 3 on this, this 3 right here. Okay, imagine that's on the other side, and I've still got my finite sum here. So the question now is, what do I do with this sum? Well, it might not look like anything familiar, but actually I want to tell you that this is something that is somewhat familiar to us. So it's just a little bit in disguise. So remember this thing where if I take 1 over 1 minus x squared, it's equal to the sum n equals 0 to infinity of n plus 1 x to the n. This is a little bit awkward though, because I don't want to use the variable n because, well, the n is playing a different role in my sum. But let's use another variable I, right? It doesn't matter what the variable is called, of course. So 1 over 1 minus x squared is equal to the sum I equals 0 to infinity of I plus 1 x to the I, where of course the I plus 1 comes from I plus 1 choose 1, right? Okay. The sum up at the top might not look like that right now, but we can do a little substitution to make it look a bit more similar to that. So there's different ways I could do this. The way I'm going to do it now is I'm going to make a substitution by letting I be equal to n minus k. So if I is equal to n minus k, of course that means that k is n minus I. So my sum becomes negative 3 to the n minus I, because that's k is n minus I, times n minus k, which is n minus I, which is just I. Now we have to be a bit careful here to recognize the limits of our summation. So the sum is going to go from I equals 1 to n. The reason is that k equals 0 if and only if I is equal to n. So the bottom limit of the sum becomes the top limit here of n, and k is equal to n minus 1 if and only if I is equal to 1. So that explains the reason for these two limits of the summation. They come from the upper and lower limit of the original summation. Okay, so our sum is equal to this. Okay, this is not looking that much, that similar to our original sum, or the sum at the bottom. But let's do a little bit of shifting things around. So if I shift my indices a bit, you can think of this as starting at I equals 0 and going to n minus 1, negative 3 to the n minus I minus 1, I plus 1. Okay, now at least we've got the I plus 1 that we want. Okay, let's now do a bit of factoring and pull out negative 3 to the n minus 1. Then what we're left with is negative 3 to the negative I plus 1. And the sum is again from 0 to n minus 1. Okay. Of course, a negative exponent is just like taking a reciprocal. So this is equal to negative 3 to the n minus 1, sum I equals 0 to n minus 1 of negative 1 over 3 to the I times I plus 1. Okay. Now we've got a finite sum, which we can write as a difference of two infinite sums. So this is negative 3 to the n minus 1 times the infinite sum 1 over 1 minus negative a third all squared on the bottom minus x to, so it's not, there's no x, but my x is negative a third to the n over the same thing, 1 minus negative a third all squared. Okay. This is because, this finite sum is just the infinite sum we have below minus x to the n times that infinite sum where x is equal to negative a third. Okay. Now you could do some simplifying and stuff. You don't necessarily have to. So we've got bn is equal to negative 3 to the n times b0, which was 42, plus negative 3 to the n minus 1, 1 minus a third, that's minus negative a third is 4 thirds squared. Oh, I don't know what this is, but it's, 4 thirds 1 over 4/3 squared. I'm just doing the algebra here. Minus so negative 1/3 to the n over that same thing, 4/3 squared, and whatever. I mean, you can simplify this if you want. I'm not going to do it, but this is your final answer. I should perhaps make a comment here about general solutions to recurrence relations versus specific solutions. So the recurrence relation that we were dealing with here is Bn equals -3 Bn minus 1, I think plus n. Let's double check. Right. Bn is -3 Bn minus 1 plus n. Okay, so if I wrote this down for you and I said, find the general solution, well, that would be basically the same thing I've got above, except for we wouldn't have any b0 to plug in. So the general solution would be -3 to the n b0 plus -3 to the n minus 1 times this stuff here. So if you're ever given a first order recurrence relation and you're asked to find the general solution, basically the idea is you can do this telescoping thing, but the point is at the end you're not going to have any b0 to plug in because we're trying to find a general solution with no initial conditions. So you just leave it in this form. However, if you want to find the specific, find the particular for the initial condition b0 equals 42, then you plug in 42 for b0 and you get what we had above. So so this kind of highlights the difference between a particular solution and a general solution. So the general solution will always have some unknown in it, probably based on some early term of the sequence or something. But well, that's in the case of first order recurrence relations. But in second order recurrence relations, we're going to have a different thing going on. But yeah, basically, you just have a b0 in your formula. But if it asks you to find the particular solution, then there should be no remaining, things like unknowns like b0. It should just be a function of n, which is, like the formula we have at the top. Okay, so hopefully these examples help. Basically, whenever you're solving a first order recurrence relation, this method is going to work most of the time. Well, at least it's going to work in this course all of the time. But the basic thing is, you need to know how to set up the telescoping sum. And then once you've set up the telescoping sum and you sum it all up, you sum the left side, sum the right side. On the right side, you might get some kind of a complicated thing like this. Okay. And you've got to know how to figure that out. Right? And that's always going to involve some of these things we know about generating functions. So it could be this one, it could be 1 over 1 minus x cubed, or it could be, actually there's not really that many options. I mean, it's basically it's always going to boil down to one of these things, and you've got to be able to figure out a formula for that sum. Okay, so just to clarify the steps of this procedure, what do? We first set up a telescoping sum by writing the recurrence equation with, let's say our sequence is an, so an and an minus 1 on the same side. Two, we sum up the telescoping sum and you sum up both sides of the equation. So on the left side, it just gives you something. So left-hand side will be in terms of an and a0, or if your recurrence started at a1 or something, a1 if recurrence starts at 1. Right-hand side might be a complicated looking sum. The third step, though, is to do some substituting to get the sum to look like one of these things we understand, which is like 1 over 1 minus x to the k, which equals, of course, sum n equals 0 to infinity, n plus k minus 1, choose k minus 1, x to the n, right? It probably won't be an infinite sum like this, but if you can write it as a finite sum with this kind of form, then you can always write the finite sum as a subtraction of two infinite sums, and that's how you're going to, in most cases, this is how it's going to work. Okay, so see you in the next video.